let's look at the completed velocity versus time graphs and see how we can calculate the displacement or change in position that occurs, and then we'll check them against the position time graph information to the left. All right, the idea is that the area between the velocity time graph line and the time axis, that area is equal to the displacement. So delta x displacement equals area. Well, I have an odd shape here. I'll just break it down into two rectangles. This is, if you just count the squares here, it's a 2 by 1, or it has an area of 2. And here, these are 1/2 a unit high right there. So half times 1 is a half, and another half is 1. So that's an area of 1, and that would be an area of 1. So all told, there is an area of 2 plus 1 plus 1, or 4. And the units are going to be meters in this case. If I assume that this is velocity in meters per second, and this is time in seconds, the units will be meters. Let me explain why the units are meters for displacement. We're taking these areas of these rectangular shapes, and on the vertical is the velocity in meters per second. On the horizontal is some number of seconds. And we multiply one side by the other, we have to multiply the units, and that would be meters per second times second. And the seconds cancel out, being just meters. So that's why these units are meters. And that makes sense for displacement. Change in position should be measured in meters. And now we just want to check, is this 4 meters correct? Did this object change its position 4 meters? If we go back to the position versus time graph, you see that its starting position is position 0, and at time equals 5, it's right there at the 4 meter mark. So it went from 0 meters to 4 meters, or 4 meters. So yes, that does match up. The displacement shown on the position versus time graph matches the displacement calculated from the area of the velocity versus time graph. Let's draw the next one. Here's an area. Now this is above the time axis, so these are positive areas, but graphical area can be negative, which is just for graphical area. And this area, because these values down here are negative, these sides of this rectangle here is going to be negative, giving a negative area. So the idea again is delta x, change in position, otherwise known as displacement, is equal to the area. Here is an area of 2 meters. So it's going to equal 2 meters for that. And then plus this area, which is going to be, one side is a minus 1.33, repeating, and this side is 3 seconds. So this area right here is minus 1.33 meters per second times 3 seconds. The seconds cancel, leaving just meters, and 1.33 times 3, that's actually equal to 4. So I'll add that, and it's a negative 4, right, because that is a minus sign there. This is minus 4. So the change in position equals 2 meters plus minus 4 meters, or minus 2 meters. Is the total change in position according to the area of the VT graph. Does that match up with what we see over here? Well, the object starts actually at 2 meters, that's its starting position, and when it's done at 5 seconds, it's at 0 meters. So that is indeed a decrease of 2 meters on the position axis, which agrees with our calculation here.